Hello everyone. So today I am going to discuss with you one of the most important topic, that is Diels Alder reaction. And in every year, if you follow the questions, then you will find that lots of questions are coming from Diels Alder reaction. And from that topic, from that Diels Alder reaction, one of the basic part constitute the nature of the diene and dienophile. How the substituent and how the conformation of the diene controls the reactivity and as well as regioselectivity is the today's topic that I am going to discuss with you. So let's discuss the diene and dienophile. So before I go to the how the nature of the diene and dienophile controls the reactivity and regioselectivity and other thing, I would like to mention one point which corresponds to my previous video, that is 4n plus 2. If my pi electron system in thermal condition, it is always allowed, that is Supra Supra. So 4n plus 2 thermal, definitely in thermal Supra Supra, it is allowed Supra Supra. Whereas if you find a system 4n and it is given h nu, it is allowed, that is Supra Supra. So as I have already told, that Supra Supra condition is the criteria to give our reaction, to give the product. So 4n plus 2 is a thermal, normally general, Supra Supra will give the product, whereas 4n in photochemical condition will give the Supra Supra condition to give my product. For example, let me say one example. Let's say, for example, they have given a system like this, that is both are same. This is also 4 pi, this is also 4 pi, and they have given condition of thermal. So they are asking that if my it is 1,3-butadiene 2 molecules, if react in thermal condition, what will be the product? So but just by watching this condition, the thermal, you have to find in your mind that it will be 4n plus 2, not 4 pi plus 4 pi, because in that case it will be 8 pi, that is 4n system. So in this case the reaction will be like this, that is 4 plus 2 cycloaddition. Okay, it is not the case like this. There will be something option like this to confuse you, a system like this, that is 8-member system. So just by watching you, that is thermal condition. So if it is my thermal condition, then it will be the allowed reaction. I mean my orbital symmetry allowed reaction is the 4n plus 2 Supra Supra. That's why if my both are same diene, it is not this condition, that is H, it is not given H nu, that's why it will not happen. Rather it will go 4 plus 2 cycloaddition to give this product. And if they given H nu, then it will react 4 plus 4, that is 8 pi system, to give the corresponding product. Okay, that's it. Now let's discuss the today's topic, that is the important part here. The topic today I choose because the previous GATE exam, that is 2019, just few days have gone. So depending upon the basic concept of the nature and diene and dienophile, they have asked question. And another question from 2018 December, you will find 1-2 marks question that the same concept has been asked. As well as if you see previous jam, I have already seen that there are questions from this topic, that is nature of the diene and dienophile. That is the important part. Okay. So there are basically two important aspects in to control over the reaction, selectivity, regioselectivity, whatever. And the two aspects are, one is electronic effect and another is steric effect. So the point is how the electronic effect present in my diene and how the steric effect, otherwise you can say conformational effect, controls the diene and dienophile's nature to over the reaction. That's the point you have to remember. So the point is steric or the conformational, how the controls, and the electronic part. Let's see some examples. So as you know, it is the diene and it can have substituent in several positions. So if I first consider the electronic part, if it is my diene and it have a substituent either in one position, say X, or in two position, one in one position terminal and another is X, where X is an electron releasing group. Okay, so my reaction is favored if X is an electron releasing group which increases the electron density on this system. The reaction is favored for the Diels Alder reaction. Why? Because it reduces the homo-LUMO gap of the homo-LUMO gap between the diene and dienophile. So the criteria is that generally it is the electron releasing group that gives a favorable condition for the Diels Alder reaction. This is the nature of the substituent on diene. On the other hand, if in my dienophile there is an electron withdrawing group EWG, if it is an electron withdrawing group, it favors for the decrease in the homo-LUMO gap, homo of the diene and LUMO of the dienophile. That is, the point is, if my dienophile contain an electron withdrawing group, so the effect of this is the reduction in the homo-LUMO gap, so the reaction is favored. So the reduction in homo-LUMO gap is generally a criteria for overall. What I am trying to say is that it's not the only case that X, which is an electron releasing group, and EWG in dienophile can lower the homo-LUMO gap. The vice versa is also possible, and that is called inverse electron demand effect. For example, what I am already told that X here electron releasing group in diene, electron withdrawing group in dienophile reduces the homo-LUMO gap. It is possible in another way. How? If the case is like that, if my substituent here here is EWG, and in my dienophile it is the electron releasing group, electron releasing group, then also the reaction is favored. How? Because in this system also the homo-LUMO gap increases. But the difference, the important part is that now in this system it is the homo of the dienophile. So the important part, it just have been reversed, inverse electron demand effect. So if my dienophile have electron releasing group, then it's homo, and my dienes in which electron withdrawing group is there, its LUMO will take part in reduction, will take part in reaction, because in this case, that is my dienophile's homo and electron withdrawing groups, the diene's LUMO gives us a condition with a lower homo-LUMO gap. That's why it's called inverse electron demand Diels Alder reaction. So the point, let me clear with you once again, that general case is that if my diene contain an electron releasing group and dienophile contain electron withdrawing group, that is normal Diels Alder reaction, it is favored because it gives the diene's homo and dienophile's LUMO in a lower difference. The other case, that is inverse electron demand, is the just opposite of that. In that case, it is the electron releasing group in dienophile, that's its homo, and electron withdrawing group of diene, its LUMO, gives us a condition for favorable reaction. So this was all about the electronic part. Now let's come to the conformational part, or you can say the steric part also. The point is that you have to find, suppose I have a diene. Okay, so that's how I have drawn for the first few minutes. But it's not the only conformation. It can have a conformation like this. So there are two names are there. This is called, you can see easily, that is cis type. It is cis type. That's why it is called S-cis. Whereas it is trans type, so it is called S-trans. So this is two type of conformation one can have in a diene. Now the point is that for a reaction, that is Diels Alder reaction, what we need is the conformation S-cis. So this is the conformation by which the reaction takes place, not the S-trans conformation. If there are some several kind of dienes are there, and one of them can't have S-cis conformation, then it will not go under reaction. S-trans doesn't go Diels Alder reaction. It's very important part you have to remember. Now let's some effect on, that is substituent. How substituent on, say one position, not one position, I mean terminal position, or in second position, how they control over the reaction rate and the reactivity. For example, I have written in my notebook. I will share with you. For example, let me first take this. So this is conformation, that is S is conformation. It will react with a dienophile. I am not drawing dienophile. I am writing here X. When my X is an hydrogen atom, simple 1,3-butadiene. Whereas if I take here methyl group, and the other case if I take a tertiary butyl group, the effect here which controls the reaction, my methyl group increases the electron density in the 1,3-butadiene. So homo-LUMO gap decreases in this system. That's why it's react faster compared to 1,3-butadiene. So if the rate for this as a normal, we can take 1, whereas the rate increases here, it becomes 4.2. But the effect, if you say, oh, it's a tertiary butyl group, it will react faster, but this is not the case. Because of steric reason of this tertiary butyl group, the reaction of this diene with dienophile gets slower. Even the rate of is 0.025. Okay, so this is one of the important part that you have to find. So there are two parts, electronic part as well as steric part. Here from 1,3-butadiene to 4-methyl butadiene, 4-methyl 1,3-butadiene, the reaction rate increases because of electronic effect. Whereas coming to this part, in which the steric part takes control over the reaction and it gives a slower rate. Now let me take another example which clarifies this problem. The problem here is given like this. I have a system like this, that is 1, 2, 3, 4, 5, that is 1, 3. It's a pentane system in which 1,3-butadiene. Okay, no problem. Now I have a system like this. That is here a methyl and methyl. They may ask a question like that, which will react faster. You can easily predict that there are two hydrogen. So because of this methyl and hydrogen steric repulsion, this will react slower compared to this system where no steric repulsion is there. So this will react faster compared to this system. Let me take another example. So in the previous example, I have shown the effect of substituent on the terminal position. If my terminal position contain an electron releasing group. Now let's take an example in which I have substituent on this 2 position. Say, let's say methyl. What is the effect of this compared to my normal substituent, diene, that is 1,3-butadiene. The case here is, the rate is here much faster. Why? Because of the electronic effect, because of the electronic effect, because it increases the electron density. So it's as we have already told, that's favor the reaction. But the point is that, now coming to the point, if I increases its 2, that is like this system, it is also favored much more compared to this. Will have higher reaction rate compared to this system. Okay. Now let me show an example. For example, if I have a tertiary butyl rather than a methyl group, what will be the effect? If I have only one tertiary butyl group in the 2 position, let me draw. So I have already told that there is an effect of conformation. So in this conformation, that is S conformation, there is less steric repulsion compared to the S trans. Let me show how this is. So I have drawn here S trans conformation in which I have a 1 tertiary butyl group. There is a hydrogen and hydrogen. So you can see easily that the separation between the tertiary butyl group and the hydrogen atom in the S conformation is larger, because 120, whereas in the conformation S trans, this is S trans conformation, the tertiary butyl group and the hydrogen comes to in a close approximation. So it is not this conformation, it's equilibrate with this conformation compared to this. So it easily undergoes the Diels Alder reaction. Now let's make it little bit tricky. Now if they give a substituent in both this position, for example tertiary butyl. Now the case is just reverse. It increases the it favors the electronic effect, but this is not the case. In the S-cis conformation, there is a higher steric repulsion because of tertiary butyl. It's not the hydrogen, so it doesn't prefer this conformation. So it generally what happens? It undergoes this conformation, that is S trans conformation. That's why it never undergo Diels Alder reaction. Okay. Now let me discuss some question which have been asked in the CSIR and GATE also. Before I go to the question, I have one more example that I have to share with you. For example, if they give a substituent like this, CH2 and CH2, and they may ask, sorry, there will be double bond. If they ask, will it undergo Diels Alder reaction or not? So you may think that why not in double bonded CH2 in double bonded CH2, it will undergo Diels Alder reaction. But this is not the case. How? We have to remember that there is a lone pair of nitrogen. See, so because of cross approximately in the S-cis conformation, this doesn't favor the S-cis conformation, whereas it prefers the S-trans conformation in which the nitrogen lone pairs are opposite to each other. Okay. So this is the S-trans conformation. That's why it doesn't undergo Diels Alder reaction. I think this is a pretty good example. One more example is trivial and you can understand very easily. If I have a system like this, conjugated alkyne, so it also can't undergo Diels Alder reaction because it can't have a S-cis conformation like this. It is impossible because there is a 180-degree angle. It can't just have a 120-degree angle. This kind of system also can't undergo Diels Alder reaction. There are more of this kind of example. Let me show it one by one. For example, if you have a system in which the double bond is fixed, it can't have the S-cis conformation. System like this, it is properly fixed, rigid system. It can't give my S-cis conformation. System like this, it also can't have a S-cis conformation. So that's why this kind of system doesn't undergo Diels Alder reaction. And depending, this aspect has been asked in the GATE as well as JAM and also CSR. So I will discuss the three questions, two questions. The questions they have asked is like this. They have given butyl, tertiary butyl, let's say A, and system like this. They have given tertiary butyl and a system like this, that is here butyl tertiary and butyl tertiary. I have already discussed partly this example. They have asked what will be the rate of this diene to a Diels Alder reaction. So just by looking at the three options, you can easily understand that I have already told also that this system, that is 2 tertiary butyl, 1 2 I say, so it can't have a S-trans conformation, S-cis conformation, because it will have a steric repulsion between the 2 tertiary butyl group. So it's favor this S-trans conformation, so it can't undergo Diels Alder reaction. So C will have slowest rate. And among these A and B will favor S-cis conformation. How? I have already shown. Let me show it again. If I write it like this, there is a steric repulsion. So if dienophile comes, there will be a more steric repulsion between this system. It will not prefer this conformation. Rather, it will favor this kind of system. So now the separation between the tertiary butyl and hydrogen is more. So this will undergo faster reaction compared to A, in which it just there is no effect like this kind of system. So that's why it will be B will have higher rate compared to A, and C will have lowest rate. Okay. Now let me take another question, and this type of question is very much common in the sense that they prefer like this kind of question. They will give you several diene, and among them they will ask how many of them will show Diels Alder reaction and how many will not, whatever they can say. And these are been in JAM and GATE as a NAT, and you know NAT is very much important. I will draw the system whatever they have given. So they have given like this, and a system like this, system like this, pretty trivial. And last but not the least, this. So they have given how many option? 1, 2, 3, 4, 5, 6, 7. They have given 7 different diene, and they have asked how many of them will undergo Diels Alder reaction. So I have already told it's the S-cis conformation that's give the preferred conformation for Diels Alder reaction. So if you can see easily that it is also S-cis, it will undergo Diels Alder reaction. It is fused, not fused. It is the cyclopentadiene. The diene has to be S-cis. It can't have S-trans. So it is also give Diels Alder reaction. Whereas this is S-trans and it can't have S-cis conformation. It will not undergo Diels Alder reaction. It is also S-cis. It will undergo Diels Alder reaction. Here also the case. Whereas it can't be S-cis conformation, so it can't undergo Diels Alder reaction. And here again also S-cis. So overall among these 5 is the correct answer. That is the 5 of them will undergo Diels Alder reaction. So this is been asked in 2019. I mean just the year. GATE. Even if you see JAM and CSR net, the concept about the diene and dienophile, how they control the reaction, is the important part. So till now I have discussed what about the diene, how the substituent and the conformation controls the reactivity. Now let's come to the point of dienophile. I am talking just about the substituent, how it's controlled. And I already told the more the electron withdrawing group present in a diene, it's favors the Diels Alder reaction. Sorry, it's the dienophile. More the electron withdrawing group in a dienophile, it favors the reaction. Okay. Now here I have drawn 4 systems A, B, C, D, in which A has 4 cyano group. That's why it will have, compared to this, which have 2 cyano group, it will have a faster rate. That is A has a faster rate compared to B. Now let's come to the point about C and D compared to this system. It's little bit tricky, just watch carefully. Here there is a conjugation between oxygen lone pair and the carbonyl group, whereas in this system there is a carbon, that is p pi orbital from this system and conjugation with this system. Okay, since these are both having cross conjugation, okay, but here the oxygen 2p orbital with carbon 2p orbital, so there is a little bit less conjugation compared to this, in which there is a carbon-carbon conjugation. So there is a more conjugation. So the electron withdrawing effect to this pi system. So because this conjugation is more compared to this, because of the difference in whereas same carbon-carbon orbital, whereas here a carbon-oxygen orbital. So here conjugation is more. That's the effect of electron withdrawing group to this dienophile part is less, whereas effect of this is electron withdrawing group is more compared to this. So it will have a better electron withdrawing effect on this dienophile moiety. That's why C will have a faster rate compared to D. Okay, so the answer will be like this. Now let's come to a generalization point after discussing so much example with you. I hope this will be very useful for you. So it is the electron releasing group in the diene and electron withdrawing group in dienophile that controls the reaction and the rate. Okay, one more thing is important. It is the S-cis conformation that is necessary, and it has to be for to participate in Diels Alder reaction, and in the S-trans conformation it can't undergo Diels Alder reaction. So this was all about the nature of the diene and dienophile, how they control the reactions of that is Diels Alder reaction. I hope you find it very useful, and thank you for watching and stay with us. Thank you.